SwayamPrabha. Digital India. Educated India.
So, welcome to the next lecture in the course of rapid manufacturing, which is focused towards rapid prototyping processes. In the concept of rapid manufacturing, rapid prototyping plays a very major important role, or in the era where rapid manufacturing is going on, rapid prototyping processes are playing a very major role and a major share. In order to understand rapid prototyping process more in detail, we will first see the science or the principle behind these processes. So, first we will try to see polymerization, that is photopolymerization. Then we will see photopolymerization of materials. Then we will see reaction rates, and then we will start looking into various processes, stereolithography, and we will see a machine in stereolithography. Then what are the different scan patterns, vector scanning, then mask projection photopolymerization process, then at last it will be 2-photon stereolithography processes. When we talk about rapid prototyping, so it is very clear that it is rapidly you are supposed to make prototypes. So, when you are rapidly supposed to make prototypes, it primarily depends upon what is your starting material. And the next thing is, what is your starting form of material. So, what is the starting material? You can have a polymer, you can have a ceramic, you can have a metal. Okay. And the starting form material can be a solid, can be a liquid, of course you can also have gas. But since the thickness whatever you make is going to be very less in gaseous form, so we do not take this gaseous as a predominant starting form of material to do prototyping. So, now it is very clear you can have polymer material, ceramic material, metals, and they can exist in solid form and liquid form. Again, I will try to classify in solid form also three things. It can be in powder form, it can be in filament form, it can be in sheet form, basically 0D, 1D, 2D. Liquid form, as you know, it is very easy for processing. Okay. So, now what is happening is, when you choose the material, correspondingly we have to choose how can I join these materials together such that you can form a prototype. So, basically here what we do is, the polymer which exists in liquid form is chosen, and here what happens is, when we wanted to convert a liquid into a solid, there is a process which happens to convert the liquid into a solid, is called as photopolymerization, is called as first solid. A liquid to solid is polymerization. If it initiates or activates or happens because of the presence of photo, that means to say light, it is called as photopolymerization. When you try to take a polymer and a powder form, you can use laser, so it will be more of selective laser sintering. If you take it as metal, it can be selective laser sintering or selective laser melting. When you try to take filament, it can be polymer if it is like you take it to a viscoelastic state, allow it to cure, or when you take metals also, you can try to apply heat and convert this filament into a droplet, and droplet is again converted into a 3D form to give a shape to it. So, depending upon the starting material, the rapid prototyping process cost, time, accuracy depends. So, with this basic fundamental understanding, let us keep moving. So, as I told you, polymerization. Polymerization is, what is polymer? It is poly plus mer. So, it is several of these mers joined together to form a polymer. So, the process of joining several of these mers to form a polymer is called as polymerization process. If the polymerization process can be initiated by a presence of light, it is called as photopolymerization. Photopolymerization makes use of a liquid, radiation crucible resin or a photopolymer as their primary material. A photopolymer or a light activated resin is a polymer that changes its property when exposed to light, often in the presence of UV light or visible region of an electromagnetic spectrum. Most photopolymers react to radiation in the UV range of wavelengths, but some visible light systems are also used. So, predominantly it will be UV based. So, you take a UV light. So, basically you can take a UV lamp or you can take a UV laser for curing it. We prefer UV laser because you can have fine resolutions in the developed material. Upon irradiation, these materials undergo a chemical reaction to become a solid. This reaction is called as photopolymerization and is typically complex, involving many chemical participants. Photopolymers were developed in the late 1960s and soon became widely applied in several commercial areas, most notably the coatings and printing industry. Many of the glossy coating on paper and cardboard, for examples, are photopolymerization. So, this is a liquid polymer. Here you can see blue small dots are called as monomers, and along with the monomers you have this violet one are called as oligomers, and then we have photoinitiators which are green, and when the UV light hits on it, you can see these mers are trying to form a network with oligomers. They are trying to form a oligomer, and the photoinitiator are used to start the reaction and form this bond between them. So, because of the bond forming, this is the bond, this tries to make it into a solid. As I told you, this UV can be from a lamp or it can be from a laser. And when I talk about lamp, so you will not have your exposure area many a times will be over a large area or it will be along a single line. But when I talk about laser, it will always be a spot. So, this has more higher resolution. So, I would like to prefer having a UV laser for doing this photopolymerization. So, it is very clear from this diagram, the mers and the oligomer joins together by a bond by this process. Photocurable resins are also used in dentistry, such as for sealing the top surface of the teeth to fill in deep grooves and prevent cavities. In these applications, coatings are cured by radiation that blankets the resin without the need of patterning either the material or the radiation. This changed with the introduction of stereolithography. Stereolithography is a process. It is also interesting if you go back and look at it. Stereolithography. Lithography is light for making 2D structures. If I want to make a 3D structure, so I call this process as stereolithography. Lithography means you have a light wherein which this light is exposed on top of a mask. So, light exposed on top of a mask, this is a mask, and then you have some material, this material is getting, the mask is getting transferred, you have a photopolymer. So, because of the light exposure you get this photoresin. On curing, it tries to create this structure. In the mid 1980s, Charles Houle was experimenting with UV curable material by exposing them to a scanning laser similar to the system found in the laser printer. He discovered that solid polymer patterns could be produced. By curing one layer over a previous layer, he could fabricate a solid 3D part. So, one layer is nothing but a 2D layer. So, by curing one layer over the previous 2D layer, he got a 3D part made. This was the beginning of stereolithography, which is otherwise called as SL technology. The company 3D Systems was created shortly thereafter to market SL machines as rapid prototyping machines to the product development industry. So, you can quickly develop. Why quickly you can develop? The process starts it from CAD, it goes to the machine, and these machines are rapid prototyping machines wherein which you get the output. So, this try to reduce the cycle of product life cycle. So, since then a wide variety of SL related processes and technologies have been developed. The various types of radiations may be used to cure commercial photopolymers, including gamma rays, X-ray, electron beam, UV, and in some cases visible light. This UV compared to electron beam, X-ray, gamma rays, there are a lot of advantage. The advantage can be the resolution can be as small as possible, but the disadvantages as it has lot of side effects, and controlling the system also becomes very difficult from the source to the workpiece. So, we always prefer to use UV light. In SL system, UV and visible light radiations are used most commonly, UV and visible light radiation. In the microelectronic industry, photomask material are often photopolymers and are relatively irradiated using far UV and electron beam. If the resolution, or if you want the resolution of the feature which is getting generated on a polymer surface to be as small as possible, for example, you want it in nanometers, then we go for electron beam, which is otherwise called as electron beam lithography. In contrast, the field of dentistry uses a visible light predominantly. This is used for curing and making the caps. The configuration that we will discuss here are vector scan or point-wise approaches typically of commercial SL machines, mask projection or layer-wise approach that irradiates entire layer at one time. We will see two photon approach that are essentially high resolution point by point approach. Although photopolymers are also used in some inkjet printing processes, which is known as the method of line-wise processing. So, the configuration can be vector scanning, can be mask projection, and two photon. Predominantly what happens is vector scanning. Mask projection is so here vector scanning means you have a point, several of these points join together to form a line, and several of these lines join to form a figure, whatever it is, right. And when I say a mask, one layer of entire information is exposed and you get it in one shot. So, that is mask projection. And two photon approach that are essentially high resolution point by point approach. So, here instead of a single photon which is used in vector scan, here we use two photons to cure it. So, this is a typical setup of stereolithography schematic diagram. So, you have a laser, this laser predominantly is UV laser, so that it can go cure the liquid polymer, passes through optics. So, this optics is for beam adjustment in terms of shape, in terms of focus diameter. Okay. So, this optics plays a very, very important role. The thing is, when we wanted to make an object which is slightly large, and if you want to move this table in a high speed, maybe 100 meters per minute or something like that. So, then what happens, the ball screw mechanism what is used, or the belt drive mechanism what is used, is not of high repeatable, or it gives you a poor repeatability. So, in order to avoid this, what we do is, nowadays we try to go for a scanning galvanometer. This galvanometer tries to sweep in one direction, it is pivoted here in one direction. So, it tries to hit at a layer of polymer and tries to cure in the X and Y plane. So, it hits and moves on the X and Y plane of a single layer. So, this once a single layer is cured, the table is moved down by a required layer thickness, or whatever you have assigned layer thickness, it sinks down. So, then once the object which is cured sinks down, now the fresh photopolymer fills on top of it. Now, again the laser hits on top of it and starts curing it. So, the repetitive curing of layer and sinking down of vat tries to help in building a 3D object. That vat is nothing but a container where a liquid polymer is held. This is a table where in which the table sinks and then new layers are getting formed. There is also a doctor's blade which is kept here. It is called as doctor blade. Okay. So, this will make sure that the layer thickness height is uniformly maintained along the surface, because in water what happens, you will always have wrinkles. So, or you will have wave patterns. So, this has to be nullified by a knife. So, this will be like this when you move the knife. Okay. So, the knife is moving. So, all the wave pattern which is there will be removed, and then you have a smooth surface. On top of it, it hits. Why? Because if you have a wavy pattern and when the laser tries to hit, there is a possibility it reflects. Okay. If it reflects, the efficiency of the process goes down. So, this is a vector scan approach. So, next technique for our discussion is mask projection technique. As I told you, there will be a mask. So, this mask you can have a static mask which is getting exposed. This is a mask which is getting exposed on a workpiece. You can do it, and this workpiece is nothing but a photopolymer. You can have a static mask, or you can have also a disc which is rotating. You can also use this as a mask and start developing the entire detail. But due to the recent developments in the electronics, we have DMDs. So, in DMDs what will happen, you will have small mirrors which are placed at the galvo. So, the laser light passes through the optics, get itself exposed, and this DMD will try to expose the complete layer as though there is a mask on top of it, complete layer on top of the photopolymer thin film whatever was there, or the liquid whichever is there, and it tries to cure it. So, this is called as mask projection approach. In mask projection approach, the complete layer of information will be exposed in one shot. So, this process is much faster than the previous process. The next process which we are going to discuss is laser photon approach, here in which we use two lasers. These two lasers hit at a single point on the liquid polymer and start curing it. So, this is what is two photon approach. Noted that in the vector scan and the two photon approach, scanning laser beam are needed, while the mask projection approach utilizes a large radiation beam that is patterned by another device. In this case it is a digital micro mirror device, which is nothing but DMD. DMD stands for digital micro mirror device. In the 2-photon case, photopolymerization occurs at the interaction of two scanning laser beams, although other configuration uses a single laser at different photoinitiated chemistry. So, although the other configurations use a single laser, both vector and even the mask use a single layer and different photo initiator chemistries. Another distinction is the need to recoat or apply a new layer of resin in the vector scan and mask projection approach, while in the 2-photon approach the part is fabricated below the resin surface, making recoating unnecessary. This is a very valid point and important, which distinguishes itself from vector and mask projection technique. As I told you, the wave pattern which is there on top of the surface of the photopolymer, if it is not made flat, the process efficiency falls down drastically. The curing does not happen properly. So, there is a possibility of defects like shrinkage or warping can happen in due course of time. In order to avoid that, in 2-photon approach, the part is fabricated below the resin surface, making recoating unnecessary. The approaches that avoid recoating are faster and less complicated. UV curable photopolymers. We are now going to talk about materials more. So, UV curable photopolymers. These are used as photoresists in the microelectronic industry. So, see, anything which happened, there will be a parallel track, as I told you, cut and paste technology. So, there were a lot of things happening in electronic industry. There were a lot of advancement happening, lot of miniaturization started, and the transistors have started adding the IC circuit. Lot of transistors were started adding the time, the processing time became a critical parameter. So, there were a lot of innovative things going on there. So, parallelly rapid prototyping also started initiating during that time. Rapid prototyping people were looking forward for material which could be used for 3D making. So, when they looked at electronic industry, they saw photoresists exhaustively used. So, initially these resists were being used for rapid prototyping. So, this application has a major impact on the development of epoxy based photopolymers. The photoresists are essentially one layer stereolithography, but with critical requirements on accuracy and feature resolution. Feature resolution is how small features you can make. The various types of radiation may be used to cure commercial photopolymers include gamma ray, which I discussed earlier, X-ray, electron beam, UV, and in some cases visible light, although UV and electron beam are most commonly used. In rapid manufacturing, many of these radiation sources have been utilized in research. However, only UV and visible light systems are effectively used in real-time product. In SL system, for example, UV radiation is used, although in principle other types could be also used. In SLA 250 from 3D system, this is a machine which is supplied by 3D system, a helium cadmium laser with a wavelength of 325 nanometer, which is in UV, is used. In contrast, a solid state laser used in the other SL model or ND-YVO4 laser is also used. In mask projection, DMD, digital micro mirror device based system, mask projection system, UV and visible light radiations are used. Thermoplastic polymers that are typically injection molded have a linear or a branched molecular structure that allows them to melt and resolidify repeatedly. In contrast, SL photopolymers are cross-linked thermosets. and as a result do not melt and exhibit much less creep and stress relaxation. So, you should now understand photopolymers used in SL process are predominantly thermosets. In thermosets, what happens? Thermoset polymers, okay? Thermoset polymers. In thermoset polymer, what happens? The branches, we will see in detail. We will see the branches carbon chain. These branches, when they form a cross link, they get so rigidly fixed and they do not give any mobility for the movement of carbon or hydrogen. So, this is a linear structure. This is a branched structure. This is a cross-linked structure. So, when you look at a photopolymer, you will have linear structure like this. Branched structure will be something like this. And when I talk about cross-link, so if you see cross-link, so here still you have a small freedom of moving. These two are not attached. You still have small freedom of moving. But here it is rigid completely. Okay. So, when a photopolymer is used, by the exposure of the UV light, when the light hits at this photopolymer, what happens is there is a cross link getting formed between the linear chains. This cross link makes the product rigid, and it is also does not have the freedom of shrinkage. Okay. So, this is what is the science behind photopolymerization. In photopolymerization, liquid polymer is used, exposure of UV light converts a linear chain into a cross-linked chain or a branched into a cross-linked chain. So, the mobility of the chains are arrested, so the strength increases. UV curable photopolymers, in the first US patent describing SL resin published in 1989, it is not very far behind, 89, now it is 2019. So, when it came into real time industry, it should have come in 99 or 97 or 96, that should be the time when it could have come in the industry. In the first US patent describing SL resin published in 1989 and 1990, the resin were prepared from acrylates which had high reactivity but typically produced weak parts due to inaccuracy caused by shrinking and curling. The acrylate based resins typically could only be cured to 46% completely when the image was transferred through the laser. When a fresh coating was put on the exposed layer, some radiation went through the new coating and initiated new photochemical reaction in the layer that was already partially cured. So, what we are trying to say, you had one layer cured, okay, and then on top of it you had a liquid which is there. So, this is a cured layer, this is a liquid on top. When the light is exposed, it tries to form a shrinkage. This layer was less susceptible to oxygen inhibition after it had been coated. So, that this is the coating which is there. So, the layer was less susceptible to oxygen inhibition after it has been coated. The additional cross link on this layer caused extra shrinkage, additional cross link on this layer, extra shrinkage which increases stress in the layer and caused curling. That was observed either during or after the part fabrication process. So, once it is done and over a period of time, the polymer starts curing over a period of time. So, when it starts curing, it started creating curling or warping and then delamination between the layers. So, please relook into these 2 points. This layer was less susceptible. What is this layer? The fresh coating was put on the exposed layer, some radiation went through the new coating and initiated new photochemical reaction in the layer that was already partially cured, right? And this layer was less susceptible. Which layer? The bottom layer, to oxygen inhibition after it has been coated. The additional cross link on this layer caused extra shrinkage. Already it has formed the cross linking. Now you put one more layer and then expose it light. This exposed light once again hits on the layer which is cured. So there is a extra shrinkage which is happening, which increases the stress in the layer and causes curling that was observed either during or after the part fabrication process. The first patent that prepared an epoxy-dyed composition of SL resin appeared in 1988 in a Japanese patent. The epoxy resin produced more accurate, harder and stronger parts than the acrylate parts. So, polyepoxy-dyed composition. While the polymerization of acrylate composition leads to 5 to 20% shrinkage, the ring open polymerization of epoxy composition only led to the shrinkage of 1 to 2%. Then people started getting away from this acrylate based photopolymerization to epoxy composition photopolymerization. This low level of shrinkage associated with epoxy chemistry contributes to excellent adhesion and reduced tendency for flexible substrates to curl during curing. So, this epoxy chemistry made a big change in photopolymerization, which is the principle when used in stereolithography process. So, from acrylate based we went to epoxy chemistry which contributes to excellent adhesion and reduced tendency for flexible substrate to curl during curing. Furthermore, the polymerization of the epoxy based resin is not inhibited by atmospheric oxygen. This enables low photoinitiator concentrations, giving low residual odor than acrylic formulations. Okay. So, this is not inhibited by atmospheric. So, it does not react with acrylic, reacted with atmosphere. Epoxy did not react with atmospheric oxygen. This enabled low photoinitiator concentrations, giving lower residual odor than acrylic formulations. However, the epoxy resin have disadvantages of slow photo speeds and brittleness of the cured part because it is thermoset. So, it will have brittleness of the cured part. The addition of some acrylate to epoxy resin is required to rapidly build part strength so that they will have enough integrity to be handled without distorting during fabrication. The acrylates are also useful to reduce the brittleness. The acrylates, so acrylates, you see epoxy, some acrylate to epoxy is required to rapidly build part strength so that they will have enough integrity to handle without distorting during fabrication. So, first what we saw was acrylate based, then we went to epoxy base, then we have a hybrid of these two. Okay. So, acrylate 46% curing, here it is 95% or 94% curing. So, here when you have a hybrid, it has a high strength. That is what it is. The acrylate are also useful to reduce the brittleness of the epoxy part. Another disadvantage of epoxy resin is their sensitivity to humidity, which can inhibit polymerization. The overview of photopolymer chemistry, the SL stereolithography photopolymer are composed of several types of ingredients: photoinitiator, reactive dilutant, flexibilizer, stabilizer, liquid monomer. Broadly speaking, when UV radiation impinges on SL resin, the photoinitiator undergo a chemical transformation and becomes reactive with a liquid monomer. So, this fellow will absorb the UV and start giving energy or start initiating the bond between the different mers. The reactive photoinitiator reacts with the monomer molecules to start a polymer chain. So, if you go back and see the previous diagram where I had beautiful star figures. These figures are photoinitiators. Subsequently, reaction occurs to build the polymer chain and then to cross-link creation of strong covalent bond between the polymer chains. Okay, covalent bonds are always strong. So, this photoinitiator, initiator means starter, photo, light. So, photoinitiator means a light which initiates. So, how does this light initiate? Somebody should have a liking towards that light. So, that fellow are called as photoinitiators. Two main types of photopolymer chemistry are commercially evident. Free radical photopolymerization, which is nothing but an acrylate. Cation photopolymerization, which is epoxy and vinyl ether. The symbol C and H denotes carbon and hydrogen atoms respectively, while R denotes a molecular group which typically consists of one or more vinyl groups. A vinyl group is a molecular structure with a carbon-carbon double bond. In this vinyl group, in the R structure that enables photopolymers to become cross-linked. So, this is what it is. So, we have talked about all these things where R, so C double bond H, we have oxygen, we have R structures, these are for acrylate, these are for epoxy, these are for vinyl ether. So, the overview of photopolymer chemistry, the most common cation photopolymers are epoxies, although vinyl ether are also commercially available. So, these two are cation based. The other one is free radical photopolymerization, which is acrylate. So, finally, it looks like you have to have a combination of epoxy, acrylate for forming a strong curable part. So, we will see in a consolidated manner UV curable photopolymers. So, UV curing resins. They are classified into two. One is acrylate radical polymerization. The other one is epoxy cationic polymerization. Okay. So, here again we have three classifications. One is epoxy denatured, epoxy denatured acrylate. The other one is urethane denatured acrylate. The last one is silicon denatured acrylate. Okay. So, thus they are categorized generally into the radial polymerization type and the cationic polymerization type. by the curing mechanism. Okay. So, the acrylate type and you have epoxy type. Epoxy type, you have two categories. One is hard type, another one is soft type. Okay. When we talk about acrylate, it is added an aerobic curing, then we will have visible light curing, then we have heat added heat curing, then last one we have is added moisture curing. So, this slide in totality talks about UV resin, acrylated, epoxy, and then what are the different kinds of it. Then two types of curing, that is acrylate type is adding anaerobic curing, visible light curing, heat curing and moisture curing. Epoxy type is hard and soft types. So, other than this we also have radial type products whose main material is silicon. So, these are the primary materials which are used in photopolymerization. So, if we wanted to compare it in terms of a table, so I will try to put it as radical and cationic. The major components it will be acrylate and then here it will be epoxy. Then if you try to talk about the curing concentration, it is 5 to 10%, here it is 2 to 4%. When we talk about curing, inhibition by oxygen, it is inhibited and this one is non-inhibited. Then after passing UV radiation, you are going to curing stops, curing continues. Then you have curing acceleration by heat. Scars accelerated. Heat resistant. This is fair and this is good. If we talk about chemical resistance, it is fair, it is good. And the last one is flexibility in resin, it is high, it is low. So, this table clearly states what is the response of different points in terms of radical and cationic. You can choose which you want for your stereolithography process. The overview of photopolymer chemistry. Free radical photopolymerization was the first type that can be commercially developed. Since SL resins were acrylate, the acrylates form long polymer chain. Once the photoinitiators become reactive, building the molecular linearly by adding monomer segments. Cross-linking typically happens after the polymer chain grows enough so that they become close to each other. Acrylate photopolymer exhibits high photo speed but have a number of disadvantages, including significant shrinkage and the tendency to warp and curl. As a result, they are rarely used now without epoxy or other photopolymer elements. When reacted, these rings open, resulting in sites for other chemical bonds. Ring opening is known as impart minimal volume change on reaction because the number and the type of chemical bonds are essentially identical before and after reaction. This is a very important point. Number and the type of chemical bonds are essentially identical before and after reaction. As a result, epoxy SL resins typically have much smaller shrinkage and much less tendency to warp and curl. Almost all commercial available SL resins have significant amount of epoxies. Polymerization of SL monomers is an exothermic reaction. Please understand, exothermic. Heat is generated during the curing process with heat of reaction around 85 kilojoule mole for an example acrylate monomer does. Despite high heat of reaction, a catalyst is necessary to initiate the reaction. So, temperature alone does not initiate, we need one more catalyst to initiate such that the epoxy type SL resins get cured and they form a solid object. The overview of photopolymer chemistry, and as described earlier, a photoinitiator acts as a catalyst. Photoinitiator. Schematically, the free radical initiates photopolymerization process can be illustrated as shown in the figure 1. P bond I is I with a free radical. So, free radical formation with M reacts and forms an initiator. I M dot, when it gets bond to several of these monomers, forms a propagation, and when this I gets to meet with an M and I which is getting there, so it gets terminated. So, this is the polymerization process, which is very important, you should understand. Radical initiates. On an average, for every 2 photons from the laser, one radical will be produced. That radical can easily lead to the photopolymerization of over 1000 monomers as shown in the intermittent steps of the process called propagation. The radial can easily lead to photopolymerization or polymerization of over 1000 monomers as shown in the intermediate steps is called as propagation. In general, long polymer molecules are preferred, yielding higher molecular weight. We don't prefer short, we always prefer long polymer or longer polymer molecules. This initiates a more complete reaction. In the previous figure, as we show, the Pi term indicates a photoinitiator and double I symbol is a free radical and M is a monomer. The polymerization process terminates from one of the 3 causes: recombination, disproportionation or occultations. Recombination occurs when 2 polymer chain merges by joining 2 radicals. Disproportionation involves essentially the cancellation of one radical by the other without joining. So, disproportionation, occultation occurs when free radicals become trapped within a solidified polymer, meaning that the radical sites remain unavailable but are prevented from reacting with the other monomer or polymer by limiting mobility within the polymer network. So, this is occlusion. The cation photopolymerization shares the same broad structure as free radical polymerization, where a photoinitiator generates a cation. As a result of laser energy, the cation reacts with the monomer. Propagation occurs to generate a polymer and the termination process to complete the reaction. A typical catalyst for a cation photopolymerization is Lewis acid such as BF3. Initially, cations for photopolymerization received little attention, but they have changed during the 1990s due to advancement in the microelectronic industry and in SL. We will now investigate the specifics of cation reaction here, but will note that the ring opening reaction mechanism of epoxy is similar to the radical polymerization. The resin formulation and reaction mechanism, the basic raw materials such as polyoxyl, epoxy dyes and acrylic acid and other esters, isocyanates etc. are used to produce monomers and oligomers used for the radiation curing. Most of the monomers are multifunctional monomers MFM or polyol polyacrylates, which gives a cross-linking polymerization. The main chemical families of oligomer are polyester acrylate PEA, epoxy acrylate EA, urethane acrylates UA and amino acrylates used as photoaccelerators in the photoinitiator systems, and cycloalipitates epoxies. Resin supplier creates ready to use formulation by mixing the oligomers and monomers with the photoinitiators as well as the other materials to affect reaction rate and part properties. In practice, photosensitizers are often used in the combination with the photoinitiator to shift the absorption towards the longer wavelength. So, we would stop here. We will continue in the next class. Thank you very much.